Before you touch RPM, run this 3-check rule. It saves jobs. Check 1. Suction integrity. Any air leak makes a pump act weak. Clamps, gaskets, fittings. Airtight matters. Check 2. Restriction stacking. Every sharp bend, reducer, and half-closed valve adds resistance. That resistance shows up as surging heat and rising RPM. Check 3. Air management. High points trap air. Air pockets break prime, cause hunting, and kill stable flow. Do these 3 checks first and your system settles down fast. Then, and only then, you adjust RPM. Want the one-page field card? Comment checks. Let's kill a myth. More flow does not automatically mean better bypass performance. Long runs, small hose, and lots of bends create friction loss. Friction loss creates pressure. Pressure creates movement, leaks, and shutdowns. Before you size a bypass, you should know the pressure you're creating. I built a friction loss quick calculator you can use on your phone. Comment pressure and I'll send it. If a bypass hose is moving, it's not harmless vibration. It's stored energy. Movement means load, misalignment, pressure searching for an exit. The fix is routing, support, and restraint. In that order. I put this into a hose routing and restraint field card. Comment route. If your pump sounds like gravel, that's not normal. That's cavitation, and it's costing you. Cavitation happens when your pump can't get enough clean, steady suction. So the water flashes into tiny bubbles, and those bubbles collapse inside the pump. That creates noise, vibration, heat, and long-term damage. The field fix isn't more RPM. It's suction discipline. Shorter suction runs, smoother bends, proper submergence, and airtight connections. If you hear gravel, stop and check suction first. Want my cavitation quick test card? Comment cav. Want fewer emergency calls? Do a 5-minute startup walk. Check 1. Suction clamps and gaskets. Airtight. Check 2. Strainer position. No vortex, proper submergence. Check 3. Discharge line, no high point air traps. Check 4. Valves, fully open where they should be. Check 5. Listen, hunting, surging, gravel sound, equal, stop and inspect. 5 minutes now prevents 5 hours later. Want my startup walk checklist? Comment walk. When a spray event happens, most crews do the wrong thing first. They rush the leak. The correct order is simple. Back people up. Reduce pressure safely. Identify the failure. Fix the cause. Restart slowly. I made a spray event response card sized for your truck or clipboard. Comment response. Most bypass failures aren't pump failures. They're path failures. When flow drops, the first reaction is always the same. Crank the RPM. Bigger pump, more horsepower. But here's the expensive truth. RPM is the symptom cover-up. If your suction has even a small air leak, if your transitions are stacking restriction, or if you've got air trapped at a high point, you can rev that pump all day and still fight the system. And while you're doing that, you're paying for it. More fuel, more wear, hotter temps, more vibration, and more breakdown risk. The fix is boring, and it works. Check suction tightness. Smooth your path. Manage the air. Because a strong pump in a bad layout will always look weak. And a smaller pump in a clean layout will look like a monster. If you want my RPM reality check checklist, comment RPM and I'll send it. Most bypass failures don't happen during flow. They happen before startup, when everyone assumes it's fine. Here are the 5 failure points I see over and over on bypass jobs. 1. Couplings that were hand-tight but never verified under load. They'll hold until pressure finds the weak gasket. 2. Hose routed through walk paths. Every step over adds movement. Movement adds load. Load finds leaks. 3. No line support. If the hose weight is hanging on the cam lock will eventually lose. 4. High points and sharp bends. That's where pressure spikes live. 5. Rushing startup. Fast pressure up turns small mistakes into spray events. If you fix these 5 before you open the valve, you prevent most failures. I put this into a one-page bypass pre-startup checklist. Comment pre-check and I'll send it. If you're sizing a bypass and you only think about flow, you'll get surprised by pressure. Here's the simple field logic. More flow plus smaller hose plus longer run equals more friction loss. More friction loss equals more pressure. More pressure equals more shaking, leaks, and failures. My quick rule: if your run is long, has lots of bends, or climbs elevation, don't just send it on hose size. Instead, estimate friction loss and pick a hose size that keeps pressure sane. Want my free friction loss quick calculator that lets you plug in hose size, length, and flow? Comment flow and I'll send it. Let's talk about the #1 reason cam locks leak on bypass jobs. It's not bad luck. It's usually one of these 3 things. 1. Wrong gasket. The gasket is flattened, torn, or the wrong material. If it's been reused too long, it's done. 2. Dirty sealing surface. Sand, grit, or debris in the groove. That tiny junk becomes a big spray at pressure. 3. Misalignment. The hose is pulling sideways on the fitting. Even a perfect gasket can't seal if the line is under side load. Quick fix. Clean the seat, replace the gasket, and support the line so the fitting isn't fighting gravity. If you want my cam lock leak triage mini guide, comment cam lock. If a bypass hose moves, it's not just vibrating, it's telling you it's loaded, and it's searching for a weak point. 3 quick fixes that reduce movement fast. 1. Route smarter. Keep hoses out of traffic and avoid tight S-bends. 2. Support the line. Don't let couplings carry the weight use blocks, cradles, or stands. 3. Restrain correctly. Whip check/restraints should be snug, placed right, and checked after pressure up. If you want my one-page hose routing plus restraint checklist, comment route. Here's a simple way to respond when you get a spray event on a bypass line without panicking. Step 1, don't rush the leak, back up. Keep people out of the line of fire. Step 2, reduce pressure safely. If you can, throttle down or shut down according to your site procedure. Step 3, identify the type of failure. Is it a coupling leak? A gasket blowout? A hose kink creating a spike? Step 4, fix the root cause. Then restart slowly. Clean the seat, replace the gasket, support the line, recheck restraints, and pressure up smoothly. Want my printable spray event response card you can keep in the truck? Comment response. A cam lock doesn't usually fail because it's broken. It fails because it's doing more than it was designed to do. If the hose weight is hanging off the fitting, you've created side load. Side load kills seals. The fix is simple. Support the hose before the coupling. Let the fitting seal, not carry weight. I made a cam lock load check diagram you can screenshot and use in the field. Comment load and I'll send it. 3 suction mistakes that cause weak bypass flow. 1. Too many fittings on suction. 2. Damaged or soft suction hose. 3. Poor alignment pulling air at connections. Fix the suction, and the pump usually fixes itself. Comment prime for the full checklist. Fast duty point estimate. No fancy tools. Confirm target flow. Estimate static lift. Add rough friction for hose length size. Add a little for fittings. That's your TDH estimate. Now you're not guessing. You have a duty point to check against the curve. Comment curve and I'll send the one-page sheet that walks this in order. Most Weak pump calls aren't pump failures. They're suction and air problems. The pump is running. The engine sounds fine, but the water just isn't moving like it should. That usually means one of three things. Air is getting in. Suction lift is too high, or the suction layout is fighting the pump. Air doesn't have to be obvious to hurt performance. A tiny leak, a loose fitting, a bad gasket. Enough to kill prime and cut capacity. Here's the rule. If a pump can't stay fully primed, it can't perform at its curve. Before you blame the pump, you should always check. Suction hose condition, connection seals, lift height, and how the suction is laid out. I put all of this into a prime and air control checklist so crews can troubleshoot fast in the field. Comment prime and I'll send it. If you want fewer leaks, fewer callbacks, and fewer "why is it spraying" moments on a bypass job, start with one thing, a 60-second walk down. Here's my quick bypass startup walk down you can do before you open the valves. 1. Couplings. Put hands and eyes on every cam lock, gasket, and safety pin. If it looks kinda seated, it's not seated. 2. Hose path. Is the discharge hose routed off the main walkway? If people have to step over it, you're inviting a trip plus a spray event. 3. Restraints. Check whip checks/restraints are actually tight and properly placed. Loose restraint equals false confidence. 4. High points. Look for kinks or sharp bends that'll spike pressure and shake fittings loose. 5. Prime plus pressure. Bring it up smoothly. If it jumps, something's wrong. Stop and verify. Do this, and you'll prevent most of the mystery leaks that waste a whole shift. Want my one-page bypass, startup, walk-down checklist? Comment walk down, and I'll send it. Air leaks don't have to spray water to cause problems. A pinhole leak can wreck prime and slash capacity. If air can get in, performance goes down. Comment prime for the air leak checklist. Quick poll for bypass crews. When a pump feels weak, what's usually the real issue? A. Air leaks. B. Suction lift. C. Hose condition. D. All of the above. Comment A, B, C, or D. If you want my prime and air control checklist, comment prime. Suction lift matters more than most people think. The higher the lift, the harder the pump has to work just to stay primed. Too much lift equals unstable flow. Comment prime for the suction setup checklist. Quick poll. When a bypass setup is wrong, what do you see first? A. Weak flow. B. Unstable pressure. C. Constant adjustments. D. Add another pump. Comment A, B, C, or D. I'm breaking down the real fix today, and it starts with the pump curve. Comment curve if you want my duty point quick sheet. Now, quick reality check. A pump that moves 2,000 GPM might only move that at low head. Add TDH, and the flow can collapse. Rule: flow on paper means nothing without head. Comment curve, and I'll send my duty point quick sheet.
3 silent bypass risks nobody respects until it bites them. 3. The discharge point under load. 2. Fittings and valves creating hidden loss. 1. No alternate route when conditions change. If your bypass depends on one discharge and one perfect plan, you're exposed. Comment discharge and I'll send my discharge risk checklist.
Most bypass pump problems are actually curve problems, meaning the pump was never matched to the duty point. Here's the truth. You don't pick a pump for flow. You pick a pump for flow at your total head. Because the same pump can do great flow at low head, and terrible flow once head climbs. So when a job shows up with weak discharge, unstable pressure, constant adjustments, we need another pump. It's usually because someone sized off flow and ignored where the pump lives on the curve. Simple check. If you don't know your TDH estimate, you don't know your duty point. And if you don't know your duty point, you're gambling. I put this into a one-page duty point quick sheet flow, TDH, and a simple curve sanity check so you don't get surprised on day one. Comment curve and I'll send it. 2 killers of bypass performance: deadhead and runout. Deadhead ills too much head, pump fights a wall. Runout ills too little head, pump runs wild and unstable. Both come from ignoring the curve. Comment curve for the quick sheet that keeps you out of both.
Bypass reality check. Backup pumps aren't real redundancy unless you have a backup plan. What happens if flow spikes? What happens if discharge backs up? What happens if power drops? If the answer is we'll figure it out, you're already behind. Comment redundant and I'll send my redundancy template. When a bypass call is urgent, I ask 5 questions every time. What's the normal flow? What's the worst case flow? Where does it discharge under load? What fails first if something goes wrong? What's the backup plan? If you can answer those, you can build a bypass that survives real conditions. I turn this into a 5-question emergency intake template you can use with crews or clients. Comment intake and I'll send it. Dry weather bypass plans lie. The second rain hits, your flow changes, and your safety margin disappears. If you don't plan a wet weather buffer, you're betting against the forecast. Comment rain and I'll send my wet weather adjustment guide. Quick field question. Be honest. When a bypass job goes sideways, what hits first? A, flow spike. B, discharge backup. C, power/fuel problem. D, prime, air issues. Comment A, B, C, or D. I'm breaking down fixes on streamline bypass pumping today. Most bypass plans don't fail because of bad pumps. They fail because nothing goes exactly as planned in the first 24 hours. Flows spike, weather changes. A valve doesn't behave, the discharge point backs up. But the plan was built for perfect conditions. Real bypass planning starts with one question: what breaks first if this job goes sideways? If your setup can't handle higher flow, partial blockage, or a quick reroute, you're not prepared. You're hopeful. I use a simple, emergency-ready bypass checklist to stress test a setup before pumps hit the ground. Comment ready and I'll send it. If you want a bypass size fast, I only need 4 numbers: target flow, discharge, elevation point, total hose length and diameter, fittings count and types. With those 4, we can estimate TDH and pick the right pump setup before we roll trucks, burn hours, or scramble on site. Most delays happen because the intake is vague. It's around here, it's not far, it should be fine. That's how you end up overspending or underperforming. I built a bypass intake mini guide you can hand to your crew or estimator so you collect the right info every time. Comment intake and I'll send it. Ask any crew that's been burned on a bypass job what they wish they had. It's redundancy, not just a backup pump, a backup plan. What happens if one pump loses prime, power drops, flow jumps beyond design? If your answer is we'll figure it out, you're already behind. Smart bypass setups build redundancy into flow capacity, discharge routing, and connections. Not just equipment count. I use a redundancy planning template to map this out before mobilization. Comment redundant and I'll send it. If you want more reliable bypass sizing, stop ignoring fittings, because every bend and valve adds head loss. A bypass plan can look perfect on length and elevation and still underperform because you built a maze of fittings. Here's what to do. Count your fittings like they're extra feet of hose. Elbows, T's, valves, reducers, log them all. Then add that loss into TDH before you pick the pump. That's how you avoid the "why is this weak" call after setup. I made a fittings loss checklist you can use on every takeoff so nothing gets missed. Comment fittings and I'll send it. Let's kill a bypass myth. Smaller hose is fine flow is flow. Nope, smaller diameter can explode your friction loss. That means your pump has to work harder to push the same water. So what happens? You lose flow, you lose pressure, or you add pumps you didn't need. Here's the simple way to think about it. You're not just moving water, you're fighting resistance for every foot of hose. Before you lock in hose size, you need flow target, run length, fittings count, and discharge elevation. I made a hose sizing cheat sheet that shows when diameter changes your outcome fast. Comment hose and I'll send it. Temporary discharge points cause more bypass issues than pumps ever will because they change, they clog, they back up, and they're rarely checked under load. If your entire bypass depends on a discharge you haven't stress tested, you're exposed. Always ask, can it handle full flow? What happens if it partially blocks? Is there an alternate route? I made a discharge risk checklist so nothing gets overlooked. Comment discharge and I'll send it. Most bypass plans don't fail because of bad pumps. They fail because nothing goes exactly as planned in the first 24 hours. Flows spike, weather changes, a valve doesn't behave, a discharge point backs up. But the plan was built for perfect conditions. Real bypass planning means asking one question first. What breaks if this job goes sideways? If your bypass can't handle higher flow, partial blockage, or a quick reroute, you're not prepared. You're hopeful. I use a simple emergency-ready bypass checklist that stress tests a setup before pumps hit the ground. Comment ready and I'll send it. Dry weather bypass plans lie to you because the second rain hits, everything changes. Inflow jumps, levels rise, your safety margin disappears. If your bypass is sized with zero weather factor, you're betting against the forecast. The fix isn't guessing higher flow, it's intentionally building a wet weather buffer into your plan. I use a wet weather adjustment guide that shows when to add capacity before storms hit. Comment rain and I'll send it. Most bypass sizing mistakes come from one sentence. Run is 800 feet, so we need a bigger pump. Distance isn't head. Head is elevation plus friction plus fittings. That's why a bypass can look perfect on paper and surge in the field. Want my quick head estimate box that stops this mistake? Comment sheet and I'll send it. Fast truth, if you don't know the flow target, you're not sizing a bypass. You're guessing. Flow target drives everything. Pump curve, hose size, and redundancy. And we'll figure it out turns into a 2 a.m. call real quick. Want my quick sheet that forces the right inputs? Comment sheet and I'll send it. Myth, add another pump. Truth, oh yeah. Fix the setup first. More pumps won't fix air leaks, more RPM won't fix vortexing, and more horsepower won't fix poor startup discipline. Setup first, equipment second. On comment, setup for the reality check. If you want a clean bypass size in the field, use this simple TDH breakdown. TDH equals static lift plus friction loss plus minor losses. Static lift is vertical difference, from your suction water level to your discharge point. Then friction loss is the tax you pay for hose length and diameter. Longer hose, more loss. Smaller hose, way more loss. Minor losses are fittings. Bends, tees, valves, reducers, each one adds head. Quick rule, if you don't know friction and fittings, you don't know your pump. You're guessing. I made a TDH calculator plus quick sheet so you can plug in hose size, length, fittings, and get a clean TDH estimate fast. Comment calci and I'll send it. Most bypass pumping problems don't start on site. They start on paper. Because people size a bypass off one number, flow. But bypass performance is flow plus total head. If your TDH is wrong, your right pump becomes the wrong pump. Here's the trap. You assume the discharge is basically flat. You ignore friction loss. You don't count fittings, and you forget the biggest wild card, where you're actually discharging to. So the bypass works, until it doesn't. Then you're chasing pressure, swapping hose, adding pumps, and losing hours. If you want to size fast without guessing, I made a bypass sizing quick sheet that forces the right inputs flow, static lift, friction, and fittings, so you don't miss TDH. Comment sheet, and I'll send it. If you want to stop bypass failures before they happen, you need 3 numbers. Not opinions, not we've done it like this before. 3 numbers. Number 1, your flow target. If you don't know the target flow, you're not sizing, you're guessing. Number 2, your head estimate. Head is not distance, it's elevation plus friction plus fittings. This is the number that turns plenty of pump into why are we surging. Number 3, your hose reality check, diameter and total length. because hose is usually the choke point. Small hose plus long run, isons, friction spike, heat, noise, and performance collapse. If you get these three right, pump selection becomes easy, and failures become rare. If you want my bypass sizing quick sheet that captures these three numbers the right way, comment sheet and I'll send it. Quick poll. What causes the most bypass headaches? A. Air leaks. B. Vortexing. C. Poor startup sequence. D. Bad hose layout. Comment A, B, C, or D. I'll reply with the fix and send the setup reality check if you comment setup. Quick poll. What causes more bypass failures? A. Wrong head estimate. B. Hose too small, too long. C. No redundancy plan. D. Air leaks. Prime issues. Comment A, B, C, D. I'll reply with the fix, and if you want my free sizing sheet, comment sheet. If your bypass is surging, noisy, or won't hit flow, look at the hose. Hose is usually the choke point. Small diameter plus long length equal friction spike. That turns into heat, noise, and a pump that looks weak. Fix the hose reality check first, then pick the pump. Want my hose reality check line on the quick sheet? Comment sheet and I'll send it. Before I quote a bypass job, I ask three questions. 1. What's the required flow? 2. What's the total head? 3. What's the failure plan at 2 a.m.? If someone can't answer those, I'm not quoting, I'm guessing. If your bypass surges, loses flow, or won't hold prime, check air before anything else. Here's the rule. If air can get in, water performance goes out. Loose cam locks, flattened gaskets, cracked suction hose, vortexing at the strainer. You can't tune around air. I list every air checkpoint in my setup reality check. Comment setup and I'll send it. Bypass truth. Hose size is a performance decision, not a preference. Undersized hose adds friction, kills flow, and makes your pump work harder. If you want my quick hose sizing sanity check, comment hose. Bypass question for the field guys. What's the most common failure you've seen? Clogging, air leaks, power issues, or bad sizing? Comment one word. I'll make a full breakdown video on the top answer. If you're quoting a bypass and you don't have these 5 things, you're guessing, and guessing gets expensive fast. Here are the 5 pieces of info I need to build a real bypass plan. 1. Required flow. What are we actually trying to move? 2. Total dynamic head, not just distance, elevation, friction, fittings, and losses. 3. Hose size plus length. Long runs and undersized hose will choke your system. 4. Power plus fuel plan. What's available on site and how long does it need to run? 5. Risk plus redundancy. What happens if the pump trips at 2 a.m.? If you want my cheat sheet, comment plan, and I'll send the 5-point bypass intake form that I use to stop mistakes before they happen. Follow for part 2, the most common head loss mistake that burns jobs. Biggest bypass mistake I see. People treat head like it's just distance. Head is elevation plus friction losses plus fittings plus velocity losses. That's why the same pump can look fine on paper and struggle in the field. Here's a bypass checklist most crews skip. Is the strainer deep enough to prevent vortexing? Is suction hose supported, not sagging? Are all gaskets seated, not just tight? Was the system primed slowly or rushed? Miss one of these and you'll chase flow all day. I put this into a 1-page setup reality check. Comment setup and I'll send it. The calmest bypass jobs are the ones that plan for bad weather. They don't scramble. They don't resize mid-storm. They already know the limits, flow surge considered, velocity controlled, head adjusted, equipment staged. I combined all of that into a 1-page wet weather bypass plan crews can reference before and during storms. Comment plan and I'll send it. Follow Streamline Bypass Pumping Consulting because rain shouldn't be a surprise. Most bypass failures aren't pump failures, they're setup failures. I see crews blame horsepower, RPMs, even manufacturers, when the real problem is upstream. If your suction is leaking air, if your strainer is vortexing, or if your startup sequence is sloppy, your pump curve doesn't matter. A good pump can look bad in a bad setup, and a smaller pump can outperform everything when the basics are right. That's why I teach setup discipline before equipment decisions. If you want my bypass setup reality check, the same checklist I use on real jobs, comment setup and I'll send it. Wet weather doesn't just increase flow, it increases head, higher discharge levels, longer effective runs, more friction from higher velocity. If your TDH calculation was tight in dry weather, it's probably wrong in rain. That's how pump curves suddenly stop lining up with reality. I use a wet weather TDH adjustment worksheet to add margin before storms expose the gap. Comment head and follow for part 5, the one-page wet weather bypass plan. Here's a dangerous sentence in bypass work. Flow should be about the same. That assumption ignores rainfall, upstream activity, groundwater, and backwater conditions. Flow is not a vibe, it's a measurement. Even a quick field check can reveal that about the same is actually 30% higher, and that difference can overwhelm hose, head, and pump capacity. I built a rapid flow verification template that lets crews sanity check flow without slowing the job. Comment flow check and follow for part 3. Why velocity quietly eats bypass capacity. Here's the most common wet weather mistake. Sizing bypass for average flow, not surge flow. Dry weather numbers feel safe, but water doesn't care what felt reasonable yesterday. When flow spikes, hose velocity climbs first, not gradually, but fast. That's why bypass systems that worked fine all week suddenly struggle after a storm. I built a flow surge multiplier guide that helps teams sanity check how much capacity they really need when conditions change. Comment surge and follow for part 3. How velocity limits disappear during rain events. Most head calculations fail in one place. They ignore everything except lift. But total dynamic head is cumulative. Friction, fittings, discharge conditions, future changes. Miss one piece, and the pump curve lies to you. That's how pumps get blamed for math problems. I created a TDH build-up worksheet that forces teams to stack head honestly before equipment is ordered. Comment head and follow for part 5, the one-page bypass plan that ties it all together. The cleanest bypass jobs aren't perfect. They're prepared. They don't rely on memory. They don't rely on assumptions. They rely on one shared plan, flow verified, velocity controlled, head accounted for, pump matched to reality. I put all of that into a one-page bypass numbers plan that PMs, supers, and rental partners can all use. Comment plan and I'll send it. Follow streamlined bypass pumping consulting, because clean numbers make calm job sites. Velocity is the quiet thief in bypass systems. You can have enough pump, enough hose length, and still lose performance if velocity is too high. High velocity means higher friction loss, more wear, and less usable head. The problem is it doesn't fail loudly, it just underperforms. That's why I use velocity targets as guardrails, not suggestions. I put those targets into a bypass velocity cheat sheet so teams can sanity check hose sizing fast. Comment velocity and follow for part 4, the head calculation mistake that keeps repeating. When rain hits, velocity is usually the first limit you break, without realizing it. Higher flow through the same hose means more friction loss, more stress, less usable head. Nothing fails immediately. Performance just disappears. That's why wet weather bypass planning isn't about bigger pumps first. It's about hose capacity and velocity control. I created a wet weather hose capacity quick sheet so teams know when they're about to cross the line. Comment hose and follow for part 4. How wet weather quietly increases total dynamic head. Most bypass plans look solid until it rains. Then flow jumps, velocity climbs, head increases, and suddenly the safe plan isn't safe anymore. Wet weather bypass failures don't happen because crews panic. They happen because surge conditions were never planned for. A real bypass plan answers this before mobilization. What happens when flow increases by 25%, 50% or more? If the answer is, we'll see what happens, the plan is incomplete. I use a simple wet weather bypass readiness checklist to stress test plans before the first drop hits. Comment rain and follow for part 2. The biggest mistake teams make when sizing bypass for dry weather numbers. One shortcut causes more bypass problems than almost anything else. Using someone else's old flow number, different watershed, different rainfall, different upstream conditions, same number, totally different reality. Field flow doesn't care what the last job did. It only cares about today's water. A 5-minute float test can expose a bad assumption before it turns into a flooded excavation. If you want my stream flow field template, distance, timing, correction factors, and GPM conversion, comment flow and follow for part 3. Why extra pump just in case isn't a real contingency. Most bypass plans look fine until they don't. And when they fail, it's usually not the pump. It's the numbers nobody wrote down, flow estimates that weren't verified, head assumptions that were never totaled, hose runs that quietly doubled friction loss. Bypass success comes down to a few hidden numbers, and if you don't surface them early, they surface themselves at the worst time. Today, I want you thinking differently. If you can't point to your flow, velocity, total head, and operating point, you don't have a plan, you have hope. I use a simple bypass numbers checklist to force these decisions before mobilization. Comment numbers and follow for part 2, the flow assumption that causes most emergency callouts. The best bypass jobs share one thing. Everyone is working from the same page. Not a spreadsheet, not a text message, a single clear bypass plan. Flow, hose, head, pump, contingencies. When that fits on one page, decisions get faster and mistakes disappear. I built a one-page bypass plan plus intake form that PMs, supers, and rental houses can all understand. Comment plan and I'll send it. Follow streamlined bypass pumping consulting, because bypass success isn't luck, it's alignment. High hose velocity doesn't announce itself. It shows up quietly. More friction loss, more wear, more noise, less actual flow. That's why 2 bypass jobs with the same pump can perform completely differently. Velocity limits aren't theory, they're guardrails. If your hose screams, your system is stressed. I put together a hose velocity quick reference that ties GPM to realistic hose ranges so friction loss doesn't steal your head. Comment hose and follow for part 5, the one-page bypass plan PMs actually use. A lot of teams say, we'll just add another pump if needed. That's not a contingency, that's hope. Real bypass contingencies answer 3 questions. What happens if flow spikes? What happens if one unit goes down? What happens if discharge conditions change? If those answers aren't written down, they won't exist when pressure hits. A smaller pump staged, a larger hose already planned, or a clear trigger point beats scrambling every time. I built a bypass contingency planning mini guide that forces these decisions before mobilization. Comment, backup, and follow for part 4, hose velocity, the silent bypass killer. Most bypass failures don't start on the job site. They start on paper, when nobody clearly defines the flow. Here's the uncomfortable truth. If your bypass plan doesn't start with a defendable GPM, everything downstream is a guess. Hose size, guess. Pump selection, guess. Fuel burn, redundancy, contingency, guess. A solid bypass plan always follows the same order. Flow first, then hose, then head, then pump. When teams reverse that order, they don't notice until the water rises, the alarms start, and someone's phone rings at 2 a.m. If you want my bypass planning order checklist, the exact sequence I use to sanity check jobs, comment order and follow for part 2. The most common flow shortcut that backfires. If your bypass line has high points, long rising mains, or weird routing, air will find you. And when it does, you get flow drop, surging, pump overheating, and crews chasing ghosts. Here's the fixed mindset. Plan the profile, identify high points, protect them. That means air release, vacuum protection where needed, isolation valves for service, and routing that doesn't trap air in the first place. A bypass can be sized perfectly and still fail if air management is ignored. Comment plan and I'll send the air high point checklist inside my starter pack. Here's a commissioning reality. Most bypass issues show up in the first 30 minutes, if you actually check the right things. My quick commissioning order: prime and verify suction conditions. Start slow, ramp up, don't slam. Confirm flow/levels match expectations. Walk the line, leaks, vibration, hot spots, weird bends. Verify alarms, auto start, and callouts. Log baseline pressure/flow so you can spot changes fast. This turns "we think it's running" into "we know it's running." Comment plan and I'll send my commissioning plus daily walk-down checklist in the starter pack. Friction loss sounds complicated until you think about it like this. Every foot of hose is a toll road, and velocity is the toll price. Two jobs can have the same pump and same GPM, but the one with smaller hose or longer run pays a bigger toll, so less energy is left to actually move water. That's why bypass plans must include length, fittings, elevation change, and discharge conditions. Quick win. If your run gets longer or you add bends, budget more head or increase hose size. Want my friction loss cheat sheet? Comment loss and follow for part 4, the pump curve trap. The fastest way to ruin a bypass plan? You size the hose by what we always use instead of hose velocity. Here's the problem. Too small a hose equals high velocity, equals huge friction loss, equals your pump looks weak even when it isn't. A simple field rule. Once you know your GPM, pick hose so you're not screaming down the line. High velocity means heat, wear, noise, and unstable control. Your pump isn't underperforming, your line is stealing head. Want my hose sizing quick sheet? Comment hose and follow for part 3. Friction loss in plain English. Most bypass plans fail for one reason: people guess the flow. And if you guess flow, you guess hose size, then you guess pump size, and now you're guessing your whole job. Here's the 60-second bypass plan I use to prevent surprises. Step 1, estimate flow fast with a float test. Pick 10 to 20 feet. Time a floating object 3 times. Average it. Step 2, get area. Width times average depth gives you a quick cross-section. Step 3, calculate flow. Area times corrected velocity gives CFS, then convert to GPM. Once you have GPM, the rest is engineering, not gambling. Hose velocity limits, friction loss, total dynamic head, and your pump curve. If you want my printable stream flow to GPM field template, comment flow, and follow Streamline Bypass Pumping Consulting for part 2. The #1 hose sizing mistake that kills bypass jobs. If you're a PM, superintendent, or estimator, here's what I want you to have before a bypass job starts. A 1-page plan that answers: what's the target GPM? What hose size and run length? What TDH are we planning for? What pump curve point are we operating at? What happens if flow spikes or the water rises? That 1 page prevents 90% of the 2 a.m. surprises. I built a bypass plan checklist plus intake form you can hand to your team, your rental house, or your client so everyone is aligned. Comment plan and I'll send it. Follow Streamline Bypass Pumping Consulting, because bypass isn't about bigger pumps. It's about a better plan. The pump curve trap is simple. People pick a pump by the headline number, then the job site head shows up and flow disappears. A pump rating without your total dynamic head is a guess. Static lift, discharge conditions, friction loss, fittings, every bit matters. Here's the safe approach. Lock your target GPM estimate, TDH, conservatively. Choose a pump that hits that point with margin and always plan for reality. Clogging, wear, fuel limits, and start/stop control. Want my bypass sizing calculator add-on? Comment pump and follow for part 5, the bypass plan checklist you can hand to a PM. Let's talk redundancy, the part everyone agrees on until it costs money. There are 2 common setups: 1 + 1 standby, 1 running, 1 ready to take over at 100% N+1, Multiple pumps sharing load with one extra pump for true spare capacity. What matters is the plan behind it. Auto start logic, alarm thresholds, who gets the call, fuel strategy, and the on-site spares that keep you running. Because the worst bypass failure isn't mechanical. It's no failover plan, and nobody knows until levels rise. Comment plan, and I'll send my redundancy plus alarm checklist inside the starter pack. Quick TDH breakdown without the textbook. TDH is basically static lift plus friction loss plus minor losses, any required discharge pressure. Here's the trap. People look at run length and say, we're fine. But friction loss stacks fast when you've got long hose runs, too many fittings, bad roading, or smaller diameter than you think. And minor losses matter. Bends, valves, manifolds, T's, they all add head. So the pump might be big enough, but at the wrong point on the curve, you're under-delivering flow, overheating, or chasing problems all night. Comment plan, and I'll send my TDH mini calculator plus the checklist so your package survives review and works in the field. Most bypass failures don't start at 2 a.m. They start at 2 p.m. when somebody says, we'll figure it out in the field. Here's the truth. If you don't lock down 4 inputs, you're guessing flow, average and peak total run length, including every segment in tie-in elevation change, and the high points that trap air discharge constraints, pressure limits, receiving structure, permits, noise. Miss just one of those and you get the classics. Wrong size, not enough head, air binding, surging, or a temporary layout that becomes a permanent headache. I'm Ed Begley with Streamline Bypass Pumping Consulting. If you want, comment plan, and I'll send you my bypass plan starter pack. The checklist plus intake form plus TDH mini calculator I use to keep bypass jobs out of chaos.